So now we're going to take that solar energy and the Earth's energy and move it around. How do we do that? We move it around in terms of heat. Heat is just transfer of energy. And temperature kind of relates to the movement of a molecule. All molecules, all atoms have motion to them. The more motion, the more excited they are, the higher the temperature is. The less motion, the lower the temperature is. That's why. Think about water. Water is a very good example of this as we go along here. So we think about water here. Water is, when it's a gas, the molecules are farther apart. They're farther apart because they're vibrating so much. Temperature is warmer. When they become liquid, temperature is cooled a little bit. So instead of boiling water, we're down a little bit cooler. They become liquid. The molecules are still moving, but they're not moving as much. Now when you go a little bit less and they become ice, the molecules are moving less, so they be frozen. So you can see the progression in water of how these motion of the molecules changes with temperature. Happens in any substance. So interestingly, temperature is directly proportional to that kinetic energy of an atom. There are other internal energies, combined potential, and other forces within a molecule. And heat is just that energy in transit when it's moving between two objects. Say you place a hand on a hot stove, you're moving that hand away really quick because heat, that hot kinetic energy that was on the stove, transferred into your hand. That was a transfer of heat. Interestingly, there are temperature gradients, changes in temperature from one location to another. It can happen up at the Great Lakes. We'll take Lake Erie as an example. There's a great temperature gradient there in the springtime. Lots of sunshine starting to come back on this side of the equator. Now the sun is, temperature shining bright over inland Ohio. However, Lake Erie is still cold. Lake Erie's temperature might be still in the 40s, but the temperature over the land may be in the 80s. That is a temperature gradient. That change, if you drove from south to north towards the Great Lake, you would be getting colder and closer the closer you get to the Great Lake. Same thing happens on the Pacific coast. Cold water out there. If I drive down through Los Angeles and arrive at a beach, temperature may drop 30 to 40 degrees. Temperature change, temperature gradient. So heat flows in response to this temperature gradient. Believe it or not, the atmosphere would like nothing better than to have the temperature exactly the same over the whole atmosphere. Doesn't happen. It's an impossibility, but that's what it would like to do. That's always going to try to do that. So warm heat will always flow from the hotter the air is towards the colder. So it always flows basically from the equator to the poles. How does it get there? How does heat transfer? Well, it does it by radiation. We've just talked about that. Conduction, convection are ways. Latent heat, phase change in water is another way. So we've just talked a lot about radiation and how you can heat up an object with energy coming there. And it's one way of energy transferring through a vacuum that none of the other methods we just talked about could do. So then there's conduction. Well, things like copper conduct heat very, very good. Aluminum does. Ice doesn't do so much, believe it or not. Or water, really even not as well. Or maybe even sand. Air, well, that doesn't conduct heat very well at all, because the atoms are so far apart in air. They need atoms close together. So conduction doesn't play a big role in heating the air, but it does heat the air that comes in contact with the ground. So if you were over a very hot blacktop road, Right at the surface, the temperature is going to be a lot warmer than it, maybe a couple feet up. That's the conduction, heating that air at the bottom. Convection is another means. And this only happens in fluids. Ever watch little bubbles form when you're boiling water and they gradually rise up to the top? That's convection. So air does the same thing. When you heat air up, it rises up, it cools, it's transported that heat up, now it's cooled, so it comes back down. That is a form of transport of heat. If you take conduction and convection, you get something called sensible heating. No water is involved in this process at this point. So that is a way of moving heat from different parts of the atmosphere, maybe from the surface upwards or even downward from the upper atmosphere down to the ground. Latent heat, whole different process. It requires energy to change state of an object. And that is water in this case. It's the only element in the atmosphere that changes state. So think about it. To make something freeze in the water, to go there, you have to lose a lot of energy. So energy is released literally as you go from a liquid to a solid, or as you go from a gas to a liquid. Energy is going out into the air. That is latent heat. If you go the other way, a solid melts and becomes a liquid. That requires heating from the environment to come into the water. So that's the opposite process. So interestingly, if it's raining outside and the air is fairly dry below that rain, as the rain falls into it and evaporates some, like if you see virga, it is actually cooling the atmosphere. But just another way of transferring heat within the atmosphere. So, because water takes a tremendous amount of energy to heat up, I live near the ocean. I love to go to the ocean. However, I also know that in the springtime, it is going to be cool when I go down to the beach. So, why is that? Because it takes a while for the ocean to heat up. In the wintertime near my house, the ocean temperatures get into the 40s. In the summertime near my house, ocean temperatures will make it by July into August into the mid to upper 70s typically, maybe even 80 if I'm real lucky. So notice, it took a long time to make that change. That's because there's so much energy required to do that. Here is just an example of all the imbalances within the atmosphere. That is complex. And if you're trying to forecast temperature accurately, every one of those that you see here must be accounted for to get the actual temperature that is going to be at your house. So that's where numerical modeling comes in, but we cannot do any of this exactly. So if you were to look at heat transfer through conduction and convection, another form of convection a lot of times produces cumulus clouds, thunderstorms. That is heat being transferred upwards from the ground into the atmosphere to warm the atmosphere up. Oh yeah, and as part of that now, we're getting condensation. So as part of condensation, you're adding another element to the heat transfer process. And here you can see how the Earth radiation coming in is not exactly distributed correctly. There's actually a surplus of solar radiation in this area. So since we know the temperature is not constantly going up in this area, that solar radiation heat must be getting transferred out of it. And as you can see here, there's a deficit the further north you get, or south. So this heat, through the exchange of air masses, through storms, hurricanes are great examples of moving a large amount of heat from the tropics into the northern hemisphere. Ocean currents. All these are ways heat is transferred. And all that imbalance is what causes a lot of the weather you see. Air masses. Think about an air mass as a huge volume of air. All right, let's take the winter time. If I have a large high pressure system sitting over Canada, and that high pressure system may be centered there most of several weeks, what is happening to that air? Well, that air is being influenced by the ground below it a lot over time. So that ground might be ice covered or snow covered. So what happens is that air is getting colder constantly, and there's no lakes or big oceans up there, so there's not a lot of moisture there. So it's getting drier. So two things are happening to that air mass. It's drying and it's getting colder. A lot of the air masses, when they come in from Canada in the wintertime, are really very cold and very dry. That's an air mass. Say the same happened over the oceans, maybe over the tropics. What are you getting? A lot of moisture and fairly humid. So air masses form in different locations, and where they form literally is going to be what type of air mass it is. So we've just talked about all the different impacts of how heat is transferred. Here, typical day at your house, day of bright sunshine. What happens in the morning? The sun comes out. Hey, we got a whole bunch of heating going on. We have a surplus. And it doesn't just stop at noon. Notice, even though the sun has reached its maximum intensity, it keeps going, so that the actual temperature will keep rising till late in the afternoon. And all of a sudden, at that point, when the temperature reaches its maximum, you begin to lose radiation. Terrestrial radiation starts winning out over the solar radiation, and it winds up cooling. You lose more in the first few hours because the temperature is warmer. The hotter the temperature, the more long-wave radiation we have. So you wind up losing more in the first few hours of temperature. Your temperature is going to cool very quickly in the evening. In the morning, for example, it may take a few hours, it may even take an hour after the sun's up before the sun gets strong enough to overcome the long-wave radiation from the Earth. So temperatures could cool for a little bit after the sun comes up. That's why sometimes low temperatures don't occur right at the instant the sun comes up, but they may occur half hour, an hour later. Interestingly, how the ground is covered impacts this. We know that snow will have a very high albedo. It keeps the air cold, and as a matter of fact, at night, it's excellent at sending out infrared radiation, so it even gets colder. However, if you have a really moist, wet area, that's not going to happen so much. So it's not going to transition as much, or cool off as much. And there are overheat islands. They did a study in downtown DC, and you can see how much warmer the actual city is than away from the city, slightly. That is because those buildings absorb heat, and they keep that heat into the evening. I used to forecast for Washington, D.C., and I can tell you, National Airport, which is downtown, is significantly warmer much of the time than Dulles Airport, which is outside of the city in a more rural environment. So I just wanted to show you one quick thing here a little bit on this. Here is today's weather map, and here's a cold front. Temperatures are in the 80s out ahead of this front, but behind it, there's some 50-degree air here. It is a cold, cold front for this time of year. So you can see here is a temperature gradient. Same thing is happening along the west coast of the U.S. And you can actually see this on satellite with temperature gradients as well. So hope you get a little bit of understanding now how temperature is going to change at your house. And let me know if you have any questions.